So I think we can start now. So yesterday we were discussing about the state space representation in its different forms. So first of all, I think I'm audible to everyone. Okay, so quickly recall that what other representations how we have selected. So we started with transfer function, which is C by R as this one. From this transfer function, we say, for example, if we go with the cascaded form. So the idea behind this writing the state space in the cascaded form is to represent this transfer function. Let's call this transfer function as t of s, as the multiplication of uh, 1 upon s plus 2, 1 upon s plus 3, and 1 upon s plus 4. And for each and every first order transfer function, we first of all we have written the signal flow diagram, and then following the procedure of selecting the states, we have finally come up with the state space representation as x dot is equal to this x, where x is a three-dimensional vector x1, x2, and x3. Okay, so this we have said as the cascaded form. For the so one thing you would notice here that the A matrix is an upper triangular matrix here. Now the second another form we have studied or we have seen yesterday very quickly is about the parallel form, where the idea is to make the partial fraction of this transfer function as the summation of uh, lower degree transfer functions. So we have expressed C of s as R of s 12 over s plus 2 plus 3 and 12 over s plus 4. Okay, and again representing it in a signal flow graph, we have obtained finally the state space representation as x dot is equal to R and y as 1 1 is x. Okay, so here in this parallel form you would notice that we have all the roots of the transfer functions in the diagonal element of this A matrix, right? Now another form we had seen very quickly yesterday is the what we have specifically called is the Jordan canonical form or canonical form. This form is basically equivalent to the parallel form, but if we have the repeated roots of the denominator polynomial, then the state space representation is called the Jordan canonical form. What I mean by the repeated roots, say for example in this transfer function you see we have three distinct roots located at -2, -2, -3, and -4. Okay, now if we have another, if we have some sort of transfer function which is let's call it Cs over Rs, s plus 3, s plus 1 square, and s plus 2. Okay, by repeated root I mean to say here in the denominator you see there are two poles located at minus 1. Okay, so you won't have all the diagonal you won't have all the roots on the diagonal elements, but there would be some off diagonal elements also. So again, using the partial fraction, I can represent this above transfer function as c by r is equal to 2 by s plus 1 square. You can do the partial fraction by yourself. S plus 2. Okay, and if I draw the signal flow diagram, I would obtain starting with r of s. So here I would have the gain 2 is, so here we would have in the integrators in the forward path where we would be closing the loop. So this is the signal flow graph I would obtain for this transfer function. Now, following the procedure uh, of writing the state space equation, I would obtain so the state space representation is just a minute, excuse me. So first of all, let's denote uh, all the elements. So this is my, maybe this color is light. Okay, let's choose it the x1. So this would become x1 dot, and since x1 dot is equal to x2 and we have the branch gain 1, so this would be my x2, meaning to say x2 is equal to x1 dot, and here I would have x2 dot. Okay, this is my x3 and this would become my x3 dot. Okay, now removing the branches with the integrators as one of the procedure. So this branch will go, this branch will go, this branch will go, and we don't have the initial conditions here, so those won't appear here. Now writing the equations, so I would have x1 dot, which is x1 dot here, this one x1 dot, so this is become equal to minus x1 plus x2. Now writing for x2 dot, I would obtain minus of x2 and plus of 2r. x3 dot as minus of 2x3 plus r, and finally y, this is my c of s, y which is equal to my c of t would be x1 minus 1 by 2 x2 plus x3. Okay, now writing it into the matrix form, I would obtain x dot is equal to and y as 1 minus 1 by 2 1 x. So you would notice here, since we have repeated roots at -1, although the roots are located at the diagonal element, but we have one where we have the repeated roots. So this is mm, a small block which is associated with the repeated eigenvalues. Okay, and the other distinct eigenvalue, or let's say the roots, is located at -2. Okay, and this is what we have in the transfer function, that the repeated roots at -1 and a distinct root at -2. Okay, so this was our Jordan canonical form. We will discuss two other important forms also, uh, which we call the controller canonical form and observable canonical form. So these two forms have some special significance in the system theory or in the control systems. We will come back to the significance of these two forms when we discuss about the controller design. But at the moment, we will see only that what are the different forms of representing the same transfer function by using the state space. Okay, so first of all, we'll take this controllable or controller canonical form. For this, we take another transfer function, let's say g by s, which is c over r, and this time we will consider some numerator polynomial also, where we have s square plus 7s plus 2, and in the denominator we have s cube plus 9s square plus 26s plus 24. Okay, so this controller canonical form is basically equivalent to your phase variable form, which we have obtained last time or in the or yesterday. So that phase variable form is basically given as and the output equation is 271 x2 x3. Okay, so this is we have obtained yesterday and we call it the phase variable form. So the controller canonical form is equivalent to the phase variable form. It's the only difference is the order of the state vector is reversed. Say, in meaning to say that reverse the if I reverse the order of the state vector here, as instead of writing x1 x2 x3, I will write it x3 dot x2 dot and x1 dot. Okay, the A matrix would remain the same. Similarly, the order here would change, x3 x2 x1 plus B would also remain the same, and the input as it is R. There won't be change in there won't be any change in the output equation. So representing it, this equation now as, let's call it this A and this call it B, x1 dot x2 dot x3 dot. So this A matrix would change now after reversing the order of the state vector. I would obtain as -9 -26 -24 1 0 0 0 1 0. Okay, and similarly the output equation would be straightforward to see after changing the or reversing the order of the state vector, this one. So let's call this as a tilde and this b tilde, and similarly this called as c tilde. Okay, and this form what we call the controllable canonical form or controller canonical form. Okay, the last form of this representation is the observer canonical form or OCF. So again consider the same transfer function. Now in this transfer function we will divide the numerator and denominator by the highest power of s, which is here is s cube. So writing this c by r of s again is by s. So this is what I obtain if I divide the numerator and denominator by the highest power of s, and here we have s cube. Okay, now take this part here and this r of s onto the right hand side. So I would obtain as 1 by s c of s. Okay, now I would combine the terms of like powers of integration, meaning to say that let's write the c of s. So this is c of s because we have 1, and I will write as 1 over s, the common factor. From the left hand side I have r, this one, and from the right hand side I have 9 and 9 of c. So if I take this 9 of c onto the left hand side, I would get r minus 9 times c. Similarly, for 1 by s square I would get 7r minus 26c, this term minus 26c, plus 1 by s cube I would get 2r minus 24c. Okay, and now I would write as 1 by s the overall bracket r minus 9c plus 1 by s, again overall bracket, as 7r minus 26c plus 1 by s as 2r minus 24c. Okay, so this is the same thing because 1 by s I have common as a factor from the overall equation. Similarly, it just to represent the integrators. Okay, after obtaining this last equation, let's write it c by s. Okay, now let's represent this equation onto the signal flow graph as, starting with the node r of s, we would have the first node as x3, this one is x2 of s, this, just a minute, just draw them separately because x3 with gain 1 would remain x3 as it is, so we won't name this node for the moment. I will go directly to x2 of s. where we have this integrator. Now draw an extra node and we get our x1, and here we have c of s and 1. Okay, now this we will let me take this onto the okay, this is better. So the first term is we have r minus 9c. So from here I would have minus 9c, and to this node we have r. So this would become r, this r minus 9c here, because x1 is equal to c. Okay. Now the second term we have 7r minus 26s. So to this node we would have 7, and from here we would have minus 26. So we have less one node less for representing this 2r. So basically this is 2 and this is we would have as the integrator. Okay, now the last term remaining is 2r minus 24c. So 2r we have here and 24c we would have as minus 24c. Okay, this is the overall signal flow graph of this transfer function. Now again from the signal flow graph we could obtain the state representation by deleting the integrator terms, and we don't have the nodes from the initial conditions. So from this diagram I would have x1 dot s minus 9x1 plus x2 and plus r, x2 dot s minus 26x1 plus x3 and plus 7r, and x3 dot s 4x1 plus 2r, and the output equation, which is c of t, is x1 only. Again representing it into the state space form, into the matrix form, we would obtain minus 9 minus 26 as x plus 1 7 2r, and the output equation is 100x. Okay, so this form we call it the observer canonical form. So you see that for the same transfer function we could use different canonical forms or different state space representation. Now particularly for this controller canonical form and observer canonical forms, they both are the duals in the sense that if you let's denote this state, this A matrix as A of uh, A of observer canonical form or AOCF. Okay, and this is BOCF, and this as COCF. Okay, for the observer canonical form. Now if I see this A tilde, B tilde and C tilde, A tilde, B tilde and C tilde for the observer canonical form. Now there is a relationship between these two set of matrices, what we call the duality, meaning to say that AOCF is basically equivalent to the transpose of A tilde matrix. Similarly, your BOCF is equal to the transpose of the C tilde, and your COCF is basically the transpose of this B tilde matrix. So this we call it the dual relationship between the observer canonical form and controller canonical form. Okay, so these are the different forms you could obtain for the same transfer function. Now, so we have seen that how we can obtain the state space representation for a given transfer function and also for a given differential equation. Now if we have the, so let's say the path what we had seen so far is the given the ordinary differential equation or the transfer function. We have seen many ways to yield a state space representation. Okay, now what we want to see, if we are given the state space representation, how we can obtain the transfer function from that representation. Okay, so this is the state equation and this is the output equation. Let's say x dot is equal to ax plus bu and y is equal to cx plus du. So taking the Laplace transform of the first equation, I would obtain Sxs. So here we have assumed that the initial conditions are 0. So x dot would become Sxs is equal to, since A, B, C, D matrices are the constant matrices, the frequency domain signals would only be applicable for the time domain signals, that is x and u, and similarly for y. Now taking this A xs onto the left hand side, I would obtain Si minus A. So this I is an identity matrix. The identity matrix is the matrix which contains 1 along its diagonals depending on the dimension of the A matrix, because S here is a scalar variable. So here I would obtain Si minus A xs is equal to Bu, and I can express xs as Si minus the inverse of this matrix Si minus A times B times U of S. Now substituting this x into this y of s, I will obtain, so you see C x is given by this Si minus A inverse B, this is Si minus A inverse Bu, plus du would remain as it is, and I can again take the U of S signal as the common factor, and the remaining term is C Si minus A inverse B plus D times U. So the overall transfer function is basically, we have seen as the ratio of the output and input signal. So if I express this as a output over input, I will obtain this transfer function. Okay, now if you have some initial conditions also, then it is not a difficult task to obtain the transfer function. You would have an extra term associated with that initial condition. Okay, so this is, you can follow. So we have discussed both the paths, given the ODE and the transfer function, how to obtain the state space representation, and now given the state space representation, how to obtain the transfer function or the ODE. And we had said that for at least for the single input single output system, we are discussing only for the single input single output system. So this would be the unique representation, but this one is not unique. Because we have already seen, first of all, many different forms of representing the state space. Okay, so this basically concludes the topic of the introduction of the state space representation and its different forms. Now if you have any questions, I can take them up. So the first question is, what is the significance of the D matrix? So the D matrix basically gives is the feed forward term. Is the feed forward term. If you see here, in the transfer function, now say suppose in this transfer function, if I have either C matrix or B, either C matrix or B matrix, either of this matrix is 0, then in that case, let's say if C is 0 or B is 0, okay, in that case I would have ys over us plus, ys over us would become equal to D, and here D is a constant matrix, meaning to say that there are no dynamics between the input and output. Okay, so this D matrix basically gives you the feed forward term. Feed forward term in the sense that the signal U directly affects the output Y, because if you have any block diagram, let's say we have this U and Y and some transfer function G of S. Okay, and this D a matrix or a constant term you would get if you have a biproper transfer function, meaning to say the order of the numerator polynomial and the order of the denominator polynomial is same. In that case only you would have this D term or the constant term. Okay, so do you have any more queries regarding this state space representation? Because from the next week we will briefly discuss about the linearization, and we'll start with the time domain analysis for both types of representations, for the transfer functions and also for the state space representations. So I see that this question was asked by Shreya and I saw her disconnect, her connection got disconnected. So maybe you could see the video later on the YouTube where I discuss the significance of the D matrix, because I'm not sure if your uh, connection is stable. So if you have more queries, then I can take them up to conclude with this topic on the state space representation. Okay, so try solving those tutorial problems. I will possibly upload the solution by tomorrow or the day after over the weekend, right? You can, I don't know if I have. Yes, those, so the submission link was already created on the Moodle, so you can also submit your solutions there for me to look at it. Okay, so I think we can close this meeting now if you do not have any queries. Okay, you can disconnect now, and then I'll disconnect.